Welcome to MEI Modelling with Algorithms. We're on the topic of Linear Programming 1, Introduction, and this is video 1.5, Visualizing 3D Linear Programming Problems. So we spent a bit of time in previous videos thinking about how we might solve 2D linear programming problems graphically. But we're going to think now about what this would look like if there were three variables. So we've now got a 3D problem. Now, you're never going to have to draw any of this sort of thing yourself, but it is important to have some sense of what it might look like if we were trying to do this sort of thing in 3D. So before we go any further, you might want to pause your video and just have a think about what a linear programming problem might look like if we were trying to represent it in 3D. So when we are representing the constraints, for example, with those lines, and those lines are intersecting at vertices, and that's forming a feasible region, and we're searching around that feasible region, maybe using an objective line, and so on. What would be the equivalent of those things if we were working in 3D? If you're good at visualizing 3D situations in your mind, then you might want to try and do that, and in a minute we'll show you what this looks like using some pictures. So what would a constraint look like if there were three variables? Well, obviously we need an extra letter for this third variable, so we'll use Z. So this is what a constraint might look like, and when we're thinking about this visually, we've got a region of space, whether it's 2D space or 3D space. There's a region of space that satisfies that inequality, and it will have a boundary given by this equation. So what does that equation look like if we were to plot it? And 3D graph plotters are available, freely available, so this is something you could play around with yourself at some point in your own time. But if I was to type that into a 3D graph plotter, what do you think it would look like? Again, if you want to, you can pause the video and think about that yourself. Well, this is it. It will actually be a plane. So here we can see our three axes, and this blue plane here represents this equation. So what to think about next is, well, what if we have several constraints? So we'll have lots of different planes forming the boundary of our feasible region. So what sort of shape, or what would the appearance of the feasible region be? Can you imagine that? Again, pause your video if you need to. So actually it's going to look something like this, obviously depending on what the constraints are. But what will happen is that we'll have these lines where two planes intersect, and where three or possibly more planes intersect, that will then give us points which form the vertices. So if you think about polyhedra, for example, they're made up of vertices, edges and faces, and that's what we can see here. And it's these vertices which are the ones that potentially we'd have to test if we were going to use the vertex method in a problem like this. If on the other hand we wanted to think about this in terms of the objective line method, well, that objective line of course will now become an objective plane. So what we can see here is this blue plane now representing the objective function for a particular value of it, and so that is cutting through the feasible region. We can see here this is where the plane is cutting through the faces of that feasible region, and then as I change what the value of the objective function is, that plane is going to move either towards or away from the origin, and at some point we'll possibly be left with a single vertex just on that boundary, and that would represent the optimal solution. So hopefully that's given you some idea of what this might look like if we were doing it in 3 dimensions, but I guess what we can take away from that is that it's going to be in practice quite difficult, to say the least, to do things that way, and if we were to try and do it with more than 3 variables, then that would become extremely difficult indeed, to say the least. So at the end of the day, what we're going to find is that we really want to move away from graphical approaches to this problem, even though they help us in some ways to think about what's going on. In terms of getting to a meaningful answer in a sensible amount of time, Really we're going to want to be looking at purely algebraic methods, and the main one we're going to see is called the simplex method, and we're going to meet that in the next topic. What we'll be doing in the final video in this topic is just laying a bit of the groundwork for the simplex method and introducing what's called augmented form. And one final thing to say, of course, is that technology is used heavily throughout this course, and so as well as having an idea of what these methods are and how they work, we're also going to see how we can use spreadsheets and linear programming solver software in order to grind through a lot of these calculations for us. So that concludes video 1.5, visualizing 3D LP problems. The final video in this section, 1.6, is going to be introducing the idea of augmented form.